Greetings. Today we will be reviewing discrete random variables, binomial, and geometric distributions. I'm Ryan Wang.
I'm Xavier Tao.
I'm Raya Yan.
So first of all, let's quickly review discrete random variables. Discrete just means we can list every possible value and the probability of each one. So like the value I get from rolling a die. The mean or expected value can be seen here. Both formulas are on the equation sheet, so you just need to know how to use them. As for transforming the variables, adding or subtracting a value from a random variable will change the measures of center and location by that amount, but the measures of spread will be unaffected. When multiplying or dividing the random variable by a value, measures of center and measures of spread will be multiplied or divided by that value. Neither types of linear transformations will change the shape of the distribution.
These are the equations associated with using the binomial distributions. But wait! You can use your calculator instead for FRQs. Remember the criteria for bins. However, you'll only need to use this when asked to verify the situation can be described using binomial distribution. Binomial and geometric settings both involve different types of discrete random variables. Pretty much all binomial settings can be boiled down to flipping a coin a chosen n number of times and counting how many heads or successes are gotten. The coin doesn't have to be 50-50, but all the coin flips have to be identical and independent of each other. Let's try an example problem. Repurposed from the 2018 FRQ number 3, we have this question. We know that this is going to be a binomial or geometric setting because we're counting the number of children who are left-handed, a binary issue. Each child is a coin, and the probability each child lands left-handed is 24%. Since we know how many children we're going to sample, this is a binomial setting. Don't forget to explicitly write out which setting this is. For context, let's define x as the number of children who are left-handed in a random sample of 60 children. At some point, we also need to explicitly state that n equals 60 and p equals 0.24. This can be done by just writing it out now, or by labeling your parameters in your calculator command. To indicate bounds, simply write p of x is greater than or equal to 9. So what's the probability? There's an equation on your equation sheet, but it's hard, so just let your calculator do it for you. We'll put in n equals 60, p equals 0.24, and 9 for lower bound, 60 for upper bound. After all, you can only have at most 60 left-handed children in a sample of 60 children. So we get a final answer of probability 0.969. But wait, there's another way of getting this answer as well. This isn't as important, but sometimes the binary distribution can be approximated by the normal distribution. To use it, the large counts condition must be satisfied. NP equals 60 times 0.24 equals 14.4 is greater than 10, and N1 minus P must also be greater than 10. So in this case, we're good. Using the equation sheet, we get that the mean is NP equals 60 times 0.24 is 14.4, and standard deviation is the square root of NP1 minus P, which is 3.308. Drawing the appropriate sketch and using the appropriate calculator function, we get 0.949, which is reasonably close to the answer you get using the binomial setting. Overall, it's easier and more reliable just to use the binomial CDF way. So don't do the normal approximation unless the test tells you to.
This is another problem repurposed from the 2011 FRQ number 3 from Form B, as you can see here. Okay, so in this problem, each flight is a coin with a 10% probability of landing on getting an upgrade. Since we're concerned with when Sam receives his first upgrade, this is a geometric setting. Let's define y as the number of times Sam will need to fly until he gets his first upgrade. To indicate boundaries, simply write p of y is greater than 2. So what's the probability? There's an equation on your equation sheet, but it's hard, so just let your calculator do it for you. We'll put in p is equal to 0.1 and 2 for lower bound, 9e to the 999 for upper bound, and using GeoCDF, we get 0.81.
As for tips and reminders for not losing points on the FRQ, remember, always define your variables. Also, state what kind of distribution it is, whether it's binomial, geometric, or normal. When you're writing the calculator function, make sure to define your variables, like what the sample size is, the number of successes, probability, upper bound, and lower bound. Make sure to state the area and direction when using CDF. This can be done by drawing a graph. Also, never forget to put context in your concluding statement. Thanks for watching, guys! Good luck on your AP exam!